Okay, so in this lecture, I'm going to introduce the matrix formulation of the linear model. This is a somewhat challenging lecture, and I don't expect everybody to understand it very deeply, but I think that this is a very useful it is very useful to have seen this matrix development once. And the reason is that once you've understood the matrix formulation, many of the other ideas automatically fall into place. For example, the contrast coding lecture will make a lot more sense if you understand how the matrix formulation of the linear model works, right? Another example of the convenience of the matrix formulation is that you can very quickly develop the analysis of variance logic without any complicated algebra, right? So it makes things much easier. So I just noticed that there's a typo in the title of this slide. I will just fix that later on. All right. So as I mentioned, this lecture is not really crucial for the course. If you don't understand many of the details, that's okay. I just want you to get a feeling for what the underlying powerful machinery there is when we turn to the matrix formulation, right? Okay, so getting on to the details here. So first of all, I want you to think about the examples that I've been discussing earlier. I have some dependent variable y and I have some predictor x, for example, relative close type or beauty level in evaluations and so on. And I want to be able to determine, at least in the hypothesis testing setting, I want to know if there's an effect of predictor x on some dependent variable y, right? So basically what we have is a situation where we have a function, right? So we can think of a function which I'll call phi, where you give it an input, the predictor x, and some coefficients beta, like beta 0 and beta 1, and this function gives you back a predicted value for y. Okay, that's what a function does, right? So if you remember, if you have something like x and y here, y can be seen as a function of x, right? So that's what we often have, like we have like some relationship between y and x can be described by some closed form equation, right? I mean, we also see this in the PDFs, right? For the random variables, like we've got different possible values in the support of x, and you've got f of x, right, which is the PDF which gives us that curve, right? So this is what functions are like, right? Okay, so that's what I'm talking about here. I'm thinking of a deterministic function phi which takes as input x and beta and gives you back some predicted value for y, right? So in the linear model setting, this is really a function. We're giving beta 0, beta 1 and x as an input into the function, and it gives us a predicted value for y, right? So we can rewrite this simple linear model in a matrix form in the following way, right? So if I have y is equal to beta 0 plus beta 1 x, as I've shown in equation 3, I could actually restate this as a matrix in a matrix form, where this term here is going to be called the model matrix, and beta 0 is going to be the parameters, the vector of parameters, right? So really what I'm going to be doing is I'm going to be writing my y as a function of x times beta written in matrix form. So this matrix formulation that you're seeing here actually is exactly the same thing as what we have here. It's not obvious, but let me show you. Oops, in matrix algebra, if I want to multiply, so this matrix x here, the x matrix, this model matrix x here is a 2 by 1 matrix, right? X is a 2 by 1 matrix. Sorry, that is not correct. X is a 1 by 2 matrix, and beta, the beta vector containing beta 0 and beta 1, is a 2 by 1 matrix, right? So in matrix algebra, multiplication of these two matrices would be like this. So you would take 1 multiplied by beta 0, right, plus beta 1 multiplied by x, right? So that is exactly the same thing as beta 0 plus beta 1x, right? That's exactly what we had earlier. So I've just rewritten the standard linear model that you had seen earlier in matrix form, right? And so we can write this more formally as a function, right? Y is a function of x and beta, right, in this way. Now, in a statistical model, so when you have actual data like the evaluation and beauty scores or the relative class data from Grodin and Gibson, we don't expect that our function will exactly fit the data. So what I mean is that if you plot the evaluation scores against beauty levels, right, you will not see a straight line like this. This is not something you will ever see in real life. Why? Because there's some variability always. That's the sigma that we're talking about, right? So there will always be, if this is the beauty and this is the evaluation, you will always see some mismatch, some variability around some fitted line here, okay? So we can't expect this function, that is this line here, to exactly fit the observed data, right? So not in a statistical model at least, right? So another example would be if you have a person's weight and height, you could find some relationship between them, but there won't be an exact straight line, right, that can exactly predict the height given the weight or whatever, right, or the other way around. So anyway, because we will never get a perfect prediction, there will be some variability around that prediction. So that's why we can think of the function that is fitting this line, this phi x of beta. We can add one more term which is some variability around that term, right? So that's what gives us this linear model framework where I've got some observed value dependent variable y, and I'm trying to predict those values from my predictor x, but there is some variability that is characterized by the random variable epsilon, as I discussed earlier. Okay, so now what we have is a non-deterministic version of the original function phi, because it is non-deterministic because there's some random variability now associated, included in this function, right? So epsilon is this error variable, the residual variability that I discussed earlier. Okay, and as you recall, the random variable epsilon was assumed to have some mean 0 and some standard deviation sigma underlyingly, right, that we estimate from the data. So that's the general linear model, and the general linear model can be written in this in terms of this non-deterministic function because of the presence of this epsilon here. Okay, this is the deterministic part, the fixed part. This is the non-deterministic part, the varying part. Okay, so the linear model is basically a non-deterministic function in this sense. Okay, right. So we can now start writing the linear model in a completely matrix form, and this makes things much more convenient in terms of developing the theory, as you will see. Okay, it's really quite magical. You will see how fast you can develop the theory now, right? Okay, so my model now is a vector of dependent variable values y. So this is really a vector that goes like this, y1, y2, all the way to yn. So it's an n by 1 matrix. And this is going to be characterized in terms of a design matrix or model matrix X, and then the vector of parameters beta, right? That's what we're going to have. So what we're going to get here now is that there will be something inside this model matrix, and there will be something inside these parameters. Inside the parameter vector, we will have the intercept and slope, etc., right? Depending on how many you have, you could have more than these, right? And then you've got the epsilons. So I've got a vector of epsilons, which will be the random variability around 0 for each of the y values in the dependent variable. Okay, now I can index each row, each of these rows I can index with j, so I can have n rows in my data frame, and so I can define the model in this matrix form now. Okay, so this is what the model is going to look like for me. So let's say I have 3 data points, right? Just for simplicity, this is what the vector of the data look like, the dependent variable which I'm writing as y here. And my model matrix now, this X matrix, is actually going to consist of 1s in the first column and my predictors x1, x2, x3 in the second column, right? And this is my beta matrix, and this thing is also, the epsilon is also a vector of 3 numbers, right? So there'll be epsilon 1, epsilon 2, epsilon 3 as a 3 by 1 matrix. Okay, so that's what this matrix formulation of the linear model looks like. And so we're going to now work with this, right? Now the predicted mean of the y values, these y scores, they will have some mean value which you can write as the expectation of the vector y, right? That's what's one common way to write that, right? So the expectation or the mean of the y scores is going to be x times beta, right? Why is that? Because if I have these 3 values, x1, x2, x3 was my X matrix, and then I've got, I don't know, I've got beta 0 and beta 1, was it, right? So if I do the matrix multiplication, I'm going to get 3 equations, right? 1 times beta 0, so that's beta 0, plus beta 1 x, and then I'm going to get beta 0 plus beta 1 x2 and beta 0 plus beta 1 x3. That's the result of this matrix multiplication, right? So so this is going to give me, each of these rows is going to give me the expectation of each of the y values, y1, y2 and y3. So right, okay, so when we have a deterministic model, right, where we have no variability at all, so we have a model like perfect fit, right? You can fit a deterministic model on top of those lines with no variability, right? This is a perfect fit, and this is basically analogous to solving a simple linear algebra problem of the form ax is equal to beta is equal to b, right? So here what we generally do is we are trying to solve for x, okay, in linear algebra, and we will generally do this kind of solution using some standard method like Gaussian elimination or something. If you have never seen this before, don't worry about it, but I want to remind you that you have seen a variant of this, right? So sometimes you will get problems like ax plus by is equal to k, and cx plus dy is equal to m or something like that, right? And you are asked to solve for x and y, right? So those are the kinds of problems that I'm talking about here. These are the kind of problems that you can solve with this Gaussian elimination procedure when you have a deterministic function. Now when you have a non-deterministic function like the ones we are talking about right now with statistical models, where you've got an epsilon involved and random variability around the fitted values, then there is no unique solution. Okay, so there is no solution as such, and so the best we can do now is to get an approximation that gets us as close as possible to the true value, right? So basically what we want to do is we want to minimize the distance between b and the elements on the distance between this and this. We want to get as close as possible to the values on the right hand side. Okay, so we want to minimize this distance, and this is exactly what we are doing when we are doing linear model fit. When we are estimating those parameters beta 0 and beta 1, we are trying to minimize the distance between the true values and the values that we are estimating from the data. Okay, so how does this work? Right, so graphically what this means is that there's a range of possible values of beta which, if multiplied with the design matrix X, with the model matrix X, they will give you a range of possible values which I'm representing through this plane. Okay, so this rectangular plane that I've got here, right, this plane here represents different possible values of X times beta, right? Now the vector of scores the dependent variable y can be represented as this vector in an n-dimensional space. Okay, if there are n data points, then you have an n-dimensional space, and the y vector can be seen as a vector in that n-dimensional space. Now there is so of the many different possible x betas that are possible, there is one set of x beta hats that are as close as possible to y, right? And we can visualize that graphically. So if you look at the plane that represents x beta, and you see the vector going off from the plane, right? The vector y is going off from the plane up into the air. So if you drop a straight perpendicular line from the y to the plane x beta, you will land in a spot which is x beta hat, which is the closest point from the end of the vector y to the plane x beta, right? So the closest point between these two vectors, right, is this x beta hat here. So this is the point that we want to reach at, right? Now it just turns out that in matrix algebra, this epsilon that you're seeing, this vector epsilon, is actually the difference between y and x beta hat. Okay, so that's how this is characterized, right? So because epsilon is defined as the difference between this vector epsilon, right, which is the line connecting the y matrix, the y vector to x beta hat, right? That can be written as y minus x beta hat, right? And so we are going to write epsilon like that, like this, and we've got another plane x beta that is now perpendicular to epsilon, right? It's at 90 degrees. This angle here is 90 degrees here, right? So you got two vectors that are completely orthogonal to each other at a 90-degree angle. Okay, so when two vectors are orthogonal to each other, the dot product of those two vectors is 0. Okay, and you can see that as an example here. So I've got one vector which is in a two-dimensional plane. I can have 1, 0 as one vector, another vector as 0, 1, right? So the dot product of this 90-degree angled vectors, right? These are perpendicular to each other. The angle between them is 90 degrees, right? The dot product of these two vectors is 0. That's a fact about orthogonal vectors that are perpendicular to each other. Okay. So if that is true, so since that is true, I can multiply x beta with y minus x beta hat, right? So for technical reasons, I'm going to have to take the transform of epsilon. So this is epsilon here, which I said is written as y minus x beta hat. So in order to do this multiplication, I'm going to take a transform, it's written like this, of the matrix y minus x beta hat. So a transform of a matrix is like this. So suppose I have a matrix like A, B, C, D, E, F, and I take a transform of this matrix. What I'm going to do is I'm going to convert the rows into columns and the columns into rows, right? So so what will happen is that, let me just do this in R quickly. Okay, so let me show you how you can play with this to get a feeling for what a transform is, right? So let's see. So let me create a matrix M, right, with let's say values 1, 2, 3, 4. Okay, so that's a nice matrix with 2 columns, right? So this is my matrix now. Let me write this M. Okay, so oops, sorry. Here's my matrix 1, 2, 3, 4. Okay, so if I take the transform of this matrix, what it does is that it converts the first column becomes the first row and the second column becomes the second row. That's what a transpose of a matrix is. Okay, right. So let's go back to my All right, so what I've done now is I'm taking the transpose of the epsilon matrix, and I'm multiplying that with x beta, and I know that that's going to be 0, and the reason that's going to be 0 is that these are perpendicular to each other, right? So that's why I have that equation here. Okay, so now I can divide both sides with beta by beta, right? So if I have y minus x beta transpose multiplied with x beta equal to 0, if I divide both sides, or let's say it's not divide, but let's say I multiply both sides with beta minus 1 here and beta minus 1 here, right? 0 times beta minus 1 is 0, and the multiplying any matrix with its inverse will give you essentially the equivalent of the number 1, right? So I can basically eliminate the beta, and that's what I've done here. I got rid of the beta by multiplying both sides with beta minus 1. Okay. Okay, so get ready now for something really exciting. So one result that I'm about to use is that when I have two matrices A and B, and I multiply those two matrices, and I have a transpose over over the entire product, right, like this here, the result of that is that you reverse the two matrices beta and B and A, the order of the two matrices, and you transpose each of them. So this is just a basic result in matrix algebra, that AB transposed is the same thing as B transposed A transposed. Okay. All right, so we're going to use this result. That's why I mentioned it. So I was at the point where I have the epsilon vector y minus x beta transpose, and I had multiplied that with the x beta matrix and said that the end result is 0 because these are perpendicular to each other, right? So now I'm going to unpack this equation. Okay, I'm going to unpack this one. So the first thing I'm going to do is I'm going to use this result here to undo this transpose that is around the bracket. So what I'm going to do is I'm going to get the transpose of yt. So y becomes y transpose because now I'm moving all the transposes inside the brackets, and because I have x beta hat here, this will now become beta hat transpose x transpose. That's because of this result that I just showed you. Okay. Alright, so now I have rewritten the first line as the second line, having unpacked the transposes that were in brackets. And now what I'm going to do is I'm going to multiply each of these. Hang on, let me just erase some of this stuff to make it neater. Okay, right, so what I'm now about to do is that right, so what I'm going to do now is that I'm going to multiply this term with each of these terms here. Okay, so once I do that, I get y transpose x, and in the second line, in the second term, I get beta hat transpose x transpose multiplied with x. Okay, now because I have this term here minus beta hat transpose x, I can add that term to both sides. If I do that, I eliminate the beta hat transpose x on the left hand side, and I get a new beta hat transpose x on the right hand side. So that's how I end up with this equation here. I've got y transpose x on the left hand side and beta hat transpose x on the right hand side. Okay, so now we're going to do something very cool. We take a transpose of both sides. That should not change anything because you're doing the same operation on both sides. So that's what I've done here. I take a transpose on both sides. Now if I do the same trick again that I showed you at the beginning of this slide, that whenever I have some terms inside brackets that are transposed, I have to flip the terms inside if I want to move the transpose inside the brackets, right? So that's what I've done here. I've got y transpose x, the whole thing transpose. I can convert that to x transpose y. Why is this x transpose y? It's because I started with y transpose x, the whole thing transpose, this can be converted to X transposed Y transpose transpose, right? So transposing a transpose brings you back the original thing. That's how I end up with X transpose Y, right? And similarly on the right hand side I do the same thing. Instead of beta hat transpose X transpose X, I end up with X transpose X beta hat. Okay, so now we are very close to the end, and you will see why this is so cool. Okay, so this has stopped working again. That's annoying. Yeah, right. So what happens now is, so where was I? I was at the point where I had X transpose Y is equal to X transpose X beta hat. So X transpose Y is equal to X transpose X beta hat. Now if I pre-multiply both sides of this matrix with X transpose X inverse, really what I will end up with is X transpose X inverse X transpose Y on the left hand side, and on this side I will get something very cool, X transpose X inverse multiplied with X transpose X beta hat, right? So what's cool here is that I have these terms cancelling out. So one fact about matrices is that if you have some matrix A and you multiply it with the inverse of that matrix, you're going to get the identity matrix. Basically you're going to get the equivalent of 1, right? So this part basically disappears because I've just multiplied a matrix with its inverse, right? With its inverse. It's just like when you divide 2 by 2, you get 1, right? So that's what's happened here. And that's how I end up with this extremely cool result, that I've got on one side X transpose X inverse multiplied by X transpose Y, that's this term here, and on the other side I've got beta hat. So what's happened is something really amazing. We have a way to estimate the beta hat parameters by simply multiplying out the model matrix or design matrix X with the observed values Y. You've got your dependent variable Y, which is a vector of scores, n times 1 matrix, and you've got your design matrix, which is a matrix with n times p, n rows and p columns, where p is the number of parameters in your model, right? And you literally multiply out the design matrix with the observed values and you get the beta hat values. How cool is that? Right? So there are some technical details that X has to satisfy certain properties. Otherwise you can't do this inversion. This inversion is not possible to do otherwise if certain properties are not met, but I think those details we can skip for now. But what is important here, the reason I made you suffer through all this, okay, is that in this equation that I've let me just erase some of this stuff. Okay, so in this equation 12 that I'm using here, I'm showing you here, this term, oops, sorry, that's not working. This term here is called the generalized matrix inverse of the design matrix X. Okay, this term, which I'm writing here as X plus, is going to become very useful to us when we think about contrast coding. It's going to lie at the heart of the contrast coding stuff that I had talked about informally earlier, the sum coding and the treatment contrast coding and so on, right? So this is where all the action is coming from the generalized matrix inverse. Okay, so you will see more details of this later on. So this is why I wanted to discuss this as in this lecture. So now I want to give you a concrete example of what a design matrix is going to look like in practice. Okay, so typically, like suppose I have a situation where I have 8 data points, so I will often have a predictor right? So I will have my 8 data points, y1 to y8, right? And so that would be my matrix Y, right? And I will generally have a design matrix that will then contain a column of ones, 8 ones in the first column, and then there will be one set of predictors in the second column and a second set of predictors in the second column. So these are examples that I've put out here. Okay, so that's what a typical design matrix will look like in our factorial designs, right? And so once I know what the X matrix looks like and the Y matrix looks like, figuring out the beta hat parameters is not going to be a problem, because we just saw the equation for how to do that. Okay. All right. By the way, I mentioned that in order to invert a matrix, you need to have full rank. So you can check the rank of a matrix using this kind of command. This is not something I'm discussing in this course. You don't need to know anything about this, but I just mention it in case you're curious about it, right? And you want to do some exploration on your own. Okay, anyway, so now our model looks like this. We have a vector of dependent variable values y, and we have our model matrix x, and we have our matrix of parameters beta, and our vector of epsilon scores, and our model can be stated in this compact form. Y is equal to x beta plus epsilon. Okay, so we are going to now write the linear model will be written in this matrix form now, right? This is what I've written here is slightly sloppy, because the epsilons that I've written here, these are written, the epsilon that I'm assuming here is describing the underlying generative process for each of the n data points, the epsilons for each of the n data points in the vector that we will have in the matrix formulation. So let me just spell this out a little bit. Here it is, right? Okay, so basically what I have is I have a matrix form of this model now. I've got n data points like y1 all the way to yn, and I've got a model matrix here. This is my X matrix, which I have ones here, and they'll have some predictor, let's say x1, x2, xn here, right? Then there will be, let's say there are two predictors, so I have beta 0 and beta 1. And now the question is, what does my epsilon look like? I've got n epsilons here, right? I've got n epsilons here. So in order to express that I have a n times 1 matrix here, right, with n epsilons here, I technically could write this part of the model specification in the following way. I could say that the epsilons are being, so each of the epsilons I could write are being generated from a normal distribution with mean 0 and standard deviation sigma. Okay, so I could write that putting an index on each of those things. Here I'm ignoring the index here. Okay, so I'm being a little bit sloppy, so you need to be careful about that. All right, so you need to be careful in the sense that if you read a stats textbook, you might see slightly more complicated presentations. Okay, so I'm just being a bit sloppy here. So all right, so we can now write the model as an alternative to this. We can write the model like this. We can say that our y, observed values y, are assumed to be generated from a normal distribution with some means x beta, right, and some standard deviation sigma. That could be one way to write this now. So some consequences of these above statements are the following. So the mean of all the epsilons, okay, so the theoretical mean of all these epsilons is supposed to be 0. Why? Because the mean of each of the underlying generative random variable is 0. It's 0, right? So that's why I say here that the expectation the expectation of the epsilons is 0. In practice, it might be slightly, different from 0 in your data sets, right? When you actually look at the residuals, calculate the mean, but the expectation in theory is 0, right? The variance of the epsilons is sigma squared, obviously, because sigma was the standard deviation for the residuals, right? So notice the way I'm writing this here, you should become familiar with this notation here. What I've done here is I've got a numerical value sigma. I'm taking the variance of that, and what I'm doing is I'm rewriting it in matrix form, right? So what I've done is I've defined a matrix with an n by n matrix, okay, with ones along the diagonal and zeros in the off diagonals. So there's zeros everywhere except along the diagonal, okay? There's zeros everywhere except along the diagonal. This is called an identity matrix. And so if I do a matrix multiplication now, right, what will I get? I will, because this is a scalar value, it's not a matrix. So I'm going to basically, if I do the matrix multiplication, I'm going to get a matrix like sigma squared along the diagonals. I'm going to get sigma squared, I'm going to get 0 everywhere else, right? So this is just a way to write the variance in a matrix form here, okay? So this, you will often see this, so that's why I mention it here. If you read a stats textbook, you might actually see this kind of formulation, so it's useful to have seen it once, okay? The expectation for y for our data will be the x times beta, which I showed you earlier, which I can write as the matrix mu, okay? So for all the y. The variance for y will be also sigma squared. Why? Because if you look at the equation, x beta has no variance, right? This is the fixed deterministic part of the model, right? It's only the epsilons that have variance, and that has a variance of sigma, right? So that's why this one has the same variance as the epsilons, okay? All right, so let's see, we can now, so now that we know all these properties of the expectation of the residuals of expectation and variance of y as well, we can now derive the expectation and variance of the estimator beta hat. Remember that beta hat is basically the mean in the sum contrast coding. Beta 0 was the grand mean and beta 1 was the deviation from the grand mean for each of the predictors, right? So these are the means in a particular sample when we do an experiment and we estimate those parameters. But you can imagine repeatedly doing that experiment, like we talked about the sampling distribution of the mean, right? So we can talk about the sampling distribution of these beta parameters now. If these beta parameters have a sampling distribution, then they have some mean and variance, right? So the variance, the standard deviation of the sampling distribution is the standard error, and it's that variance that I'm talking about here, right? So we are going to now compute these, the expectation and the variance of these estimators. That means we're going to compute the variance of the sampling distribution of these parameters, okay, under hypothetical repeated sampling. So in order to compute the variance, we need to know a fact about how to calculate variances. If you want to compute the variance of some random variable b and it's multiplied with some constant a, right, what you have to then do is to compute the variance, you have to do a squared times the variance of b, right? This is just a fact about random variable theory. If you study, basic probability theory in a textbook or something, you will encounter these proofs, okay? So but these are not something that we will ever need beyond this one thing. That's why I don't bother to teach much more about this, okay? So if you're talking in matrix algebra terms and a is not this small a, if this is not a constant value but a matrix itself, then the matrix equivalence of calculating this variance, right, of this variance here, where b is the random variable and a is some constant matrix a, then we would have to compute the variance we would be computing would be the equivalent of doing a squared variance b by multiplying the matrix a with the variance of b and then multiplying that whole product with the transpose of a. That's just the same thing as squaring the matrix a, okay? That's the equivalent of this a squared var b that I've just shown you here. So we're going to use that now, okay? this fact. So what I'm going to now compute is the expectation of the beta hat parameter. So what was the beta hat parameter? I can rewrite the beta hat parameter as the expansion that I had done earlier. If you remember, I had shown you earlier the proof that x transpose x inverse x transpose y is equal to beta hat. So I've just replaced beta hat with that term here. And one other thing to notice is that y is equal to x beta. The expectation of y is actually x beta, right? Expectation of y is x beta. So I can replace this y with x beta, and once I do that, I get something really amazing. Okay, so this is the interesting thing about matrix algebra. A lot of things get really simple once you start going through the computations. Here is x transpose x inverse multiplied with x transpose x. This thing, I'm multiplying x transpose x by its inverse. So this gives me the identity matrix, which is essentially like 1, right? So this actually gives me, this simplifies to beta. So what this means is that the expectation of beta hat is going to be the true values of beta out there in nature, which we are trying to estimate from the beta hats. Okay, so this is a way to derive. I'm showing you how you can use simple matrix algebra to derive some properties of the estimator's beta hat under hypothetical repeated sampling. Okay, so the expectation of beta hat is beta, and now I'm going to compute the variance of beta hat, right? So beta hat, remember, is the estimator. That means under repeated sampling I will get some variability in the estimates. I'm going to get that an estimate of that variability, the variance of that estimator. Okay, so I want the variance of beta hat. So what is beta hat? Again, I rewrite beta hat using that equation that I mentioned earlier, right? Now if I expand the right side out, right, what do I get? This y is the variable that will have some variance, and this thing is a constant now, right? This is going to be constant. Y will vary from experiment to experiment, obviously, right? But the design matrix is constant under repeated sampling. So this is exactly the situation that I was describing earlier. This fact about variances, that I said that if you want to do the variance of some constant a multiplied by some random variable b, you have to write a squared var b, right? And in the matrix form, if you have variance of some matrix A, constant values A multiplied with some random variable B, you would have to do A variance of B multiplied by A transpose, right? That's just the matrix formulation of that rule. And so that's what I'm doing here. Here's my A matrix, here's my transpose of the A matrix. Okay, that's all I've done here. Okay, so now it's just going to be a matter of simplifying. Okay, you can see where this is going now. Or maybe you can't, but you will see it soon, right? Now the variance of y is this term here. I just derived it a few slides ago, right? I showed it to you. Now I can now unpack the transpose of the right hand side, right? So I've got this transpose here. I've got x transpose x inverse multiplied with x transpose and the whole thing transposed, right? So how do I proceed, right? I've got in the middle, I've got the variance of y, and I've got those two guys on the left and right. I've got this term here and the transpose of this term. Where is it? Oh, have I made a mistake here? Oh, I might have made a mistake in the bracketing here, because I had so there's a bracketing error here, it seems. Let me see, what have I done wrong? Now I understand what I've done wrong, actually. So what I've done, I actually haven't made any mistake here. So what I've done is I've unpacked this transpose. So what's happened is that x transpose becomes x, that's this term here, x transpose x inverse, this term here, is going to be transposed, and that's this term here now. Okay, so that's what I did just now. Sorry, I got confused. You can see that this is not something that I do every day, so I often tend to get confused looking at these derivations. Right, so we got it now, right? So we've got, what I've done is I've unpacked this transpose, and so as I mentioned earlier, the way to unpack this transpose would be to, first of all, you reverse the order of the terms. So the second term here becomes the first term, x transpose transpose, right? And the second term, and the first term becomes the second term, which is x transpose x inverse, and the whole thing transposed, right? And that is how I end up with x transpose transpose is x, and then I have x transpose x inverse, the inverse of this, and the whole thing transposed. That's how I end up with this term here. Okay, now what's interesting is that sigma squared is a scalar value. It's just a single number, right? So we can move it to the left of the whole matrix because it doesn't require any matrix algebra anymore. We're just doing simple multiplication with a number, right? So this one is moved to the left, and so and this identity value that I had used earlier, this one here, I can actually ignore it because anything multiplied with the identity matrix gives you that number back again, right? So we can ignore that I. So what we are left with is all these x's, this jumble of x's here, right? So I've got x transpose x inverse multiplied with x transpose x. Looks interesting. And then I have x transpose x inverse transpose, right? So notice that these two terms are going to cancel out. Why? Because the first x transpose x inverse is the inverse of x transpose x, right? So what do I get left with? I get left with sigma squared x transpose x inverse and the whole thing transposed. That's what I end up with. Okay, so where was I? Yeah, where was, no, sorry, I got confused here. Yeah, right, exactly. So this is where I end up. I end up with sigma squared x transpose x inverse, the whole thing transposed. But now one thing to realize is that x transpose x inverse is a symmetric matrix. A symmetric matrix is like this, right? It's like if you got A, B, and C's on this side, right? So if I flip this matrix, I'm going to get the same matrix back. Okay, so so the transpose of this matrix is the same thing as the matrix untransposed, right? So I can remove this transpose completely, and I'm left with this neat result that that the variance of the beta hat parameters, that means of the estimators beta, is sigma squared times x transpose x inverse. Okay, so once I know the model matrix, and once I know the estimate of sigma, I can compute the variance of the beta hat estimators. Okay, concrete example. I'm trying to make this real now. So let's say I have some data from an eye tracking study where my dependent variable, which is y, is total reading time in an eye tracking study, for example. What I'm trying to find out is whether word length affects reading time. Okay, so the longer the word, the longer it should take to read that that word. Okay, so I've got word length here. I take the log of the word length, and I've also scaled the word length. So this scale function with scale equal to false as a parameter, what this is doing is it's taking the word lengths. So let's say I've got word length 1, word length 2, word length n for the n data points. I will subtract from each of these the mean word length of all this whole vector. I compute the mean of these and I subtract the mean from each of these values, right? And so what I will get as a result will be the centered word lengths. Again, this, remember, in the beauty data I had centered the beauty score such that a beauty score of 0 means average beauty level. It's the same thing here. When I centered the word length, when the centered word length is 0, that represents average word length. Okay, so I've got centered word length here as the predictor, and I fit my simple linear model, y as a function of x, right? When I fit this model, what I get as an intercept is 246, slope is 189. So this is on the millisecond scale. So I'm getting predicted, reading times here. So 1 unit increase in word length leads to 189 milliseconds slowdown in total reading time. That's what the model is telling me. Okay. Now, the model matrix X, remember in the matrix formulation, there is this model matrix X. How do I extract this model matrix from the fitted model? Well, I just use this function called model matrix and the name of the model, and it extracts this X matrix for me, right? So I've got, like I showed you earlier, I've got the columns of ones in the first column, and then I've got the predictor in the second column. Okay, this is the centered word length log scale. Okay, all right. So I'm showing you how the theory will now work out. Okay, how the theory is going to play out if we do all the calculations using matrix algebra. Okay, so what I first do is I compute the inverse x t x inverse is what I'm computing here. There's a function called solve that does this inverse calculation, and here's the transpose of x, that's xt, and then this is the matrix multiplication sign multiplied with x. Okay, so I'm just doing this calculation here, and so here's my inverse of the xtx, and then I multiply that with the transpose of xt of x multiplied by y, right? So basically what I'm doing is that calculation, beta hat xtx minus 1 xty, right? So that's what I just did by hand with some real data, and lo and behold, the beta parameters that I estimate are exactly the same. I hope now I'm right about this. 246 and 189, right? So let's go back. 246 and 189. Here are our beta parameters. So I just showed you how I would calculate these numbers. How I would calculate these numbers by hand, so to speak, using just the design matrix X and the observed values Y. It's pretty cool, right? That's how the math is working. That's how R is actually computing those intercepts and slopes for you. The contrast coding is going into the design matrix, the X matrix, and the Y is your observed value, and that's all you need to compute these scores. If you had done a different contrast coding, that would be reflected in the design matrix, and that would lead to the appropriate computations to give you the estimates for the betas. Okay. All right. So the sigma estimate, right? So the sigma that I've been talking about earlier is estimated in the model, which I can extract and call it hat sigma. So it's 239, and then I'm going to use that result that I just derived, which is sigma squared multiplied with x transpose x inverse, right? Remember, I just worked out the variance. I had just worked out very tediously and with lots of stumbles the variance of the beta hat, right? Estimators. So that's my hat var is what I'm calling it. So I've just computed the variance of the intercept and slope parameters, right? So the estimators of the intercept and slope parameters, and so what I get as a result of that is a matrix, right? So the variance is no longer a number, but it's actually a matrix, and what this matrix is showing me is the variance of the beta 0 hat estimator. Okay, so under repeated sampling, how variable is that going to be? And this term here is showing me the, sorry, I should have written it like this. This term is showing me the variance of the beta 1 hat parameter, right? So how variable will it be under repeated sampling? Okay, this estimate. The off diagonal is showing me something interesting, which I will just explain. So what this matrix of variances is showing me actually is something called a variance covariance matrix. This is called a variance covariance matrix, and this kind of matrix is used to describe a situation where you have two variables that may be correlated to each other. Okay, so you can often have a situation where you have height and weight, for example, right? Whenever somebody has a higher weight, they're also likely to have a higher height. Okay, let's assume that's true. Okay, and so there would be a positive correlation between those two things. So when you have two variables like height and weight, you can possibly have some correlation between them. And so the variance covariance matrix gives you a way to talk about that correlation. So these off diagonals, the diagonals I'd already talked about, but the off diagonals here, right, they're representing something called the covariance between the two random variables. These two random variables here, beta 0 hat and beta 1 hat, right? And the covariance is actually defined as the product of the standard deviations of each of the random variables, right, multiplied with the correlation of those two guys, right? So basically the off diagonals are giving you this quantity, the covariance. You know the standard deviations of estimates, at least, of these two random variables. You know them because these guys here, these elements on the diagonals, are giving you the variances of beta 0 hat here, and this one here is giving you the variance of, so sigma squared of beta 1 hat, right? So we know what beta 0 hat sigma hat of beta 0 hat and sigma hat of beta 1 hat is. So we know these numbers as well, and we know the covariances from the diagonal values in this matrix, so we can figure out this correlation, right? So that's what I'm going to do now. The correlation is defined like this. These two numbers are known, so we're going to figure this number out, right? So this correlation between the, okay, so this is wrong here. It should be beta 0 hat and beta 1 hat, the estimators, right? Covariance between beta 0 hat and beta 1 hat. I will fix this in the slides. I hope I remember to do that. So here we go. So we've got what this model tells us, or what these estimates tell us, is that the mean for beta 0 hat is 246 and the variance is 0.71, right? So that's what I've written here. Let's see, mean is 246 for beta 0 hat and the variance is 0.71. Similarly for beta 1 hat, the mean is this number here, 189, and the standard deviation is this number here, right? Sorry, it's not the standard deviation, it's the variance, right? Sigma squared, right? Okay, so now the covariance is given to us in this variance covariance matrix in the diagonals here. You can see these, the circled parts here, and so we can now use this covariance to compute the correlation between the two estimators, and the correlation is basically 0, right? You can see that in scientific notation this is minus 9.9 to the power of 10 to the multiplied by 10 to the power of minus 15, which is close to 0. Okay, so so what we have here is to we have got a way to talk about, yeah, let's go back and look at this for a moment and ask ourselves what we have learned from all this. What is all this giving me? Why are we doing so much work, right? Okay, so what I'm trying to show you is that all this machinery that we just worked through is giving us, for each of the two parameters, beta 0 hat and beta 1 hat, we are now able to talk about the sampling distribution of these two estimators under hypothetical repeated sampling. We can talk about the sampling distribution of these two guys. That means for beta 0 hat, if you just concentrate on beta 0 hat, we can now talk about what the variability of beta 0 hat would be under repeated sampling. The sample mean that we're getting for beta 0 hat is 246, and the variability around that under repeated sampling is the square root of this variance, 0.71979 squared will be the standard error, right? So the square root of that, sorry, why am I squaring everything? I'm sorry about that. So this is actually a variance. This is a variance. So I'm taking the square root of that variance to get the standard deviation, which is the standard error of that estimator under repeated sampling. If you remember the sampling distribution lecture, whenever we calculate a sample mean, we can talk about the sampling distribution of the mean. This is the sampling distribution of the mean that we have now figured out doing all this matrix calculations. Okay, so that's the big deal here, that we can talk about the sampling distribution of the mean for each of the parameters of interest. And we can talk about the correlation between the parameters, which I just showed you, right? So one little exercise for you guys is that in this example that I gave you, I centered the predictor, but I want you to fit the model without any centering. Okay, so this is what I just underlined here. And my question to you is, redo my matrix calculations that I showed you just now and find out what's the correlation between the sampling distribution of the intercept and slope estimators. Okay, so that's your exercise for you. And what you will find is that not centering the predictor will lead to a high correlation between the intercept and slope estimators. This fact will become very relevant to us when we start talking about contrast coding later on. Okay, all right. So this is part 1 of this lecture. I'm going to continue this lecture by talking about the likelihood ratio test and the ANOVA.